So, we have derived several nonlinear boundary value problem and initial boundary value problem to model the transport phenomena in microfluidics and hydrodynamics. Now, coming few lectures, we will talk about some outline or numerical treatment of that kind of situations. That means the nonlinear boundary value problems and partial differential equations and so on. Now, first of all, whatever the problem will be looking for the solution, numerical solutions is assumed to be well posed. Now, what is well posed can be said in a very brief manner. A mathematically well posed problem can be said in this way. That means solution exists, solution is unique, and it continuously depends on the auxiliary data. That means the initial conditions, boundary conditions, and so on. Now, we will be interested in numerical methods for boundary value problem. Now, what is boundary value problem? So, in short, boundary value problem, which is referred as BVP. Now, BVP is where the conditions are given at two different points. Say you have a differential equation y equal to f x y y dash. F is any function of this y and y dash, where y is a variable depends on x, and say x is the independent variable defined between a to b, and this is the boundary conditions y equal to say y a and y b is equal to y b. So, this kind of problems is called the 2-point boundary value problem, 2-point BVP. Now, a boundary value problem will at least will be second order differential equations, because there will be two conditions. So, obviously, the order of the differential equation will be at least 2. It can go beyond that, and consequently the number of boundary conditions also will be more. So, this is the conditions we call as boundary condition in short form in BC. So, a solution is yx is the solution of the BVP. So, what does it mean is BVP. So, if yx is the solution, means it satisfies the given differential equation and as well as the boundary conditions. This is the requirement for yx to be a solution of the given boundary value problem. Now, we are looking for numerical solution. So, numerical solution, we cannot get a solution in an analytic form, that is a function form of yx. So, what we do is we consider some discrete points, discrete points xi in xi is number of discrete points in the interval AB. That means, say we choose, if these points are equispaced, we can choose xi equal to a plus ih. I is from say 0, 1, 2 up to n. So, with our notation, x0 is a and xn equal to b, and h is the step size, which is equal to h becomes b minus a by n. N is the number of discrete points. So, these are called the equispaced point. Equispaced points. So, our intention is to get numerical solution of BVP implies finding y x at each discrete points, at each of these discrete points xi. That is, we need to get, let us find yi, which we denote, which is the y at xi for I equal to 1 to n minus 1, because y at 0 and y at n are given. So, numerical solution means we need to find out what are the yi at these discrete points I equal to 1 to n minus 1. Now, the points may be discrete. For simplicity, we have considered discrete simplicity. The discrete points are considered equispaced. Because equal interval. Now, what are the methods? So, this is our objective. Now, one of the method is the very simple one, which is referred as the shooting method. In shooting method, what I do is convert the BVP to an equivalent IBP. Now, in this boundary value problem, what is the difficulty is that we have the conditions at two different points. Now, let y dash a is given. Let y dash a is given. In that case, the problem becomes y double dash equal to f x y y dash y a equal to y a and y dash a equal to say some value, say y a dash. Okay. So, this we can treat it as a initial value problem, IVP, that is initial value problem. Now, this solution can be obtained by any method, say Runge-Kutta method. For example, I am not going to talk about Kutta method. Now, what we can do is to solve this, say let z equal to y dash and z dash equal to f x y z. So, you get y a equal to y a and z a equal to y a dash. So, solve for xi equal xi for I equal to xi when I is varying from 1 to up to n. Okay. So, in that process, because our task is to solve for all xi's when I equal to 1 to n to get yi. Now, our task is to get yi's. So, this is one of the method where we assume the if we have supplied the missing the initial condition, corresponding initial condition y a equal to y dash a. So, I can convert the given boundary value problem to a initial value problem and solve step by step starting from x equal to a. Then we go march forward and get the solution up to n. Now, these two solutions will be equivalent provided we get that y a, we get the solution by this manner at x equal to b, that means y b is equal to the given value. Okay. So, that correspondence has to be satisfied. So, in order to get an equivalent IBP, we need that the choice of the missing initial condition as such that y whatever that at x equal to that the solution for y at x equal to b becomes y b the given condition. Obviously, we do not have the idea that what the y dash a should be. So, we go in a iterative fashion. So, at each iteration, let alpha k be the missing initial condition. That is y dash a equal to alpha k. K is some number k greater than or equal to 0. We will define that what is k is. Now, with that the IBP is solved. So, obviously, this IBP, the solution will depend on the choice of alpha k. So, we denote the solution. To do that, we denote the solution of the IBP as y x I alpha k, because this y x I alpha k will vary on the choice of alpha k. To make a correspondence, we have written this as a function of alpha k. Now, for an equivalent IBP, we need that y at b alpha k should be equal to y b. Okay. So, that need to be satisfied. So, this gives a guideline to find the alpha k, the missing initial condition. So, if we define a function, let phi alpha is a function which is y b alpha minus y b equal to 0. Then the proper choice, the correct choice alpha is a root of this above equation, root of phi alpha. That means that particular alpha which satisfies this equation will be the correct choice for the missing initial condition, because for that only we get this. Now, what we do, so this gives a way how to find this alpha. So far we have not talked about alpha. What we talked, that you choose some assume some value for the missing initial condition, solve the IVP, equivalent IVP, and get the solution yxi alpha k for all these I grid points and get yb alpha k. Now, that alpha k, which is the missing initial condition, will be correct provided we get this relation. Now, this will give you, so we now construct a equation phi alpha equal to 0 defined by this way. So, this gives the clue that how to find this alpha k. Now, let alpha k and alpha k minus 1 be rather alpha k minus 1 and alpha k be two successive approximation of alpha, then we can determine the next approximation for alpha, let us call that is as alpha k plus 1 can be obtained as. So, here we apply the secant method for finding the roots. That means, we join the 2 points by a straight line, and the point where it meets the x axis is taken to be the next approximate value for the root. So, yb alpha k minus 1 by yb alpha k minus yb alpha k minus 1. So, k is 1, 2, etc. Now, we get an idea or get a guideline that how to get the missing initial condition, which should be the proper one in order to replace that IVP, in order to replace the boundary value problem BVP to a IVP. So, what we do that we choose two successive approximations. So, if I start the iteration, so say k equal to 1, so we get 0 and 1. So, alpha 0, alpha 1. So, the iteration process goes like this way. So, the iteration process starts with a choice of alpha 0, alpha 1, then obtain alpha 2 by the previous relation, by say let us call this is as equation 2, and the IVP we call as equation 1. So, by 2. Now, to get that alpha 2, what we need is we need to find out the yb alpha 0 and yb alpha 1. So, for that get by solving the IVP. Okay. So, once I get the alpha 2, so again I go back and solve this IVP, which is again if I repeat can be written as say z equal to y dash, y and z dash equal to f x y z, y a equal to y a, and z a equal to alpha k. So, every time we solve this bound IVP, this is the equivalent IVP, to get this y b alpha k. So, once y b alpha k is obtained, go to equation 2, get the next modified alpha k plus 1 and repeat the process. So, iteration process continues. Till we find that two successive approximation are very, very small or less than epsilon, say like 10 to the power minus 5 or so, less than equal to 10 to the power minus 5. So, depending on your order of accuracy, this is a small number which establish the criteria for convergence. So, this is how the shooting method goes. So, that means shooting method we can use for any sort of problems, whether it is immaterial of whether it is a nonlinear or linear problem. So, in the shooting method we replace the given boundary value problem to a equivalent initial value problem by considering a missing initial condition, assume the missing initial condition, with the missing initial condition solve this problem, go back to equation number 2 to get the successive approximation for the or the modified form of the missing initial condition, and so on. So, one of the difficulties in shooting method is how to choose these guess solution alpha 0, alpha 1. There is no clue, the problem does not know clue for alpha 0, alpha 1 are provided. And also, so these are the difficulty, and also this is a time consuming, because say for example, if I apply the fourth order Runge-Kutta method, so we have to go from A to B with few number of steps, and it will go for quite a repetition, because depending on how many k you require to satisfy this criteria. So, this will be a time consuming process. Now, one easier method, that is the most popular, are the finite difference method. So, that is our now this is the straightforward way one can solve the boundary value problem at the discrete number of points. So, again in finite difference method, what I do is we approximate the continuous functions at the discrete points, discrete number of points where we need to solve the boundary value problem, and that discrete points are referred as the grid points. So, if we consider equispaced grids, so we define, so before that, so this is the way one can outline the finite difference method. So, this method, the continuous dependent variables are replaced by discrete variables defined on grid points. A grid is a finite set of points on which we seek the values of the variables that represents an approximate solution to the differential equation. The derivatives in the differential equations are replaced by approximate finite differences, and the differential equation is therefore reduced to a system of algebraic equation. That is the most important thing. The solution of the algebraic equations then provides the dependent variable at discrete values of the independent variables. So, we consider the first we consider the linear 2-point BVP. So, the linear two-point BVP in general should be like this. Say a less than x less than b, ya equal to ya and yb equal to yb. These are the conditions are given. A, B, C are either constant or maybe some of them may be 0 or function of at the most function of x. So, we need to find y at x size at the which are the grid points defined as xi equal to a plus ih, I is 0, 1, 2, n. So, basically we need to find yi for I equal to 1 to n minus 1, because I equal to 0 and n it is given. So, at every grid point we approximate the derivative by finite differences. How we do that? Now, y I plus 1, which is equal to y at xi plus h, xi plus 1, which is nothing but y at xi plus h. Now, if I expand by Taylor series, I get y I plus h dy dx I plus h square by 2 d2i dx to I and so on. Okay. Now, I can write from here dy dx at I equal to yi plus 1 minus yi by h. So, the remaining terms will be of order h, because that is the least order terms. So, or if I write more little details, so this is will be h by 2 d2i dx 2 at I minus h square by 3 factorial d3y dx 3 and so on. Now, suppose this is plus all these terms. Okay, this is minus again, this is minus, this is minus. I am not taking the common things. So, this part is called the truncation error. Now, if I truncate this, so if I now approximate dy dx at I by y plus 1 minus yi by h, and this is the error, this will be of order h, where the truncation error is of order h. Truncation error, because we have truncated the infinite series to a finite number of terms. So, beyond these, whatever the infinite, there will be an infinite series. So, that has been chopped out. So, due to that, there is a truncation error, and that truncation error looks like is of order h, because that is the least order lowest order of h. So, if I now approximate dy dx by this fashion, that is the difference of yi at two different points, this is called the first order forward difference. Same way, one can write dy dx at I equal to yi minus 1 by h plus order h. So, this is called the first order backward difference. Now, what I did is here yi minus 1 equal to yi minus h yi dash plus h square by 2 yi double dash minus h cube by 3 factorial, this is 2 factorial, yi triple dash, etc., etc., and yi plus 1, just recall whatever we have done, h yi dash plus h square by 2 yi double dash plus h cube by 3 yi triple dash plus etc. Now, if I subtract these two, I can write yi dash as yi plus 1 minus yi minus 1 by 2h. So, this become a order h square approximation. Similarly, yi double dash can be written if I add these two. So, yi double dash can be written as yi plus 1 minus 2yi plus yi minus 1 by h square plus order h. So, here this is the way of approximating the second derivative or first derivative of higher order truncation error. Now, here we are approximating an I by using I minus 1 and I plus 1. So, that is why these differences are called central differences. Central differences. So, now we got a formula that how to replace the derivative in terms of the finite differences of the function value. So, this we will use to solve the given boundary value problem in the next lecture.